Okay. Well, we'll see if this works. So, what we will be doing today is kind of using this MLR week 7 do file. I've got a couple data sets. We probably won't get through all of them today, but we'll kind of take a look at a couple of them. I'll introduce the last topic that we'll have that's new for the exam. So that'll be related to the last question on the problem set. So we'll kind of cover that. We should take a look at how we do that in Stata, and then I'll just start kind of reviewing concepts in Stata today. Thursday and Tuesday's class, I'll probably start working a little bit more through some of those practice exam questions. So I've had that practice exam up for quite a while. I'll discuss a little bit more about the midterm at the end of class here today. But we'll kind of get going. Don't really have any housekeeping stuff other than that problem set is due at the end of the day, Friday. Okay. So I'll have office hours tomorrow. If you kind of have some last minute questions, it'd be a good time to kind of utilize those. My B251 students are tapering off, so hopefully you don't have quite as long of a wait. Any other questions for me before we just kind of dive into things here today? Okay. So once again, I apologize for the clunkiness of, of what's going to be today. So there we go. All right. So I can't see this. All right. It's going to make this more usable for me. So one thing that we kind of started talking about was as I include variables on my right-hand side to try to predict y, what should be happening to my r squared? Going up, right? Now we talked about as I add more variables, that's going to be penalized in my adjusted r squared. So the more variables that I add, my adjusted r squared is actually going to go down a little bit, right? So we'll talk about a slightly different thing here today, which is I can look at the individual significance of any one variable, right? My predicted value for any one coefficient is 0, right? I could then look at the p-value, look at the test statistic, look at the confidence interval. All would tell me whether or not I can reject that assumed true value of 0 or not. So what we're going to instead do today is let's think about a model where I've got only one variable on the right-hand side. I then include 2 additional variables. Okay? So what I want to do today is we want to compare what we call the restricted model, where I'm only including one variable, to the unrestricted, where I include all 3. Okay? So instead of just testing the significance of x2 or x3, it's testing the significance of beta 2 and beta 3. What I want to do is kind of do this joint hypothesis test. Did adding these variables in at the same time have significance simultaneously? Okay. So I want to test for whether or not the coefficients are equal to 0 at the same time. Okay. So what we're going to do, right, we can kind of think about how would I do this, right, if I had 2 variables? Well, the problem is when we think about our type 1 error or the probability that we were rejecting even though we shouldn't have been, what was that actually represented by? This is maybe more of an overarching kind of theme that would happen, would help us for the midterm. So when I'm comparing that p-value to my alpha, those thresholds for alpha were essentially the proportion of the time I'd be rejecting when I shouldn't have been, right? So I said, okay, if I'm rejecting when I shouldn't be less than 1% of the time or less than alpha 0.01, I'm okay with that, right? Because that's a really small amount of errors. So alpha was really representing our type 1 error, right? The amount of times we would reject the null even though we shouldn't be. Now, the problem is that was generally a 2-tailed test. So we thought about we had like 0.025 on each side, right? 0.025 to the right of whatever our test statistic is. It's a 2-tailed test. We had to multiply that by 2. Okay. So here the problem is if I have 2 different test statistics, what's the probability that each of those test statistics is greater than kind of that critical value? Well, the probability of each one, or essentially that p-value, would be 0.05. So there's like a 5% chance I get the rejection decision wrong on the first test statistic, that first coefficient. But if I want to test the joint significance, there's also a 0.05 or a 5% chance I'm wrong on the second one. So now the probability that I'm wrong on both would actually be 0.025. Okay? So there our alpha is not lining up with the type 1 errors we want to make. Okay? So if I'm kind of running the test for 2 statistics simultaneously, we're not getting the correct p-value, right? Instead of 5%, because we have 2 test statistics, we'd only be getting 0.025, okay? So that's not our desired type 1 error, so what are we going to do, right? So what we're going to actually have to do is use a different distribution, right? So this is going to be the F distribution. I'll pull up the table here in a second. But basically, when I add in variables, we said we know that the R squared is going to go up. So I don't have a two-tailed test anymore. I know that when I add in more variables, I can only ever see the R squared go up. So I'm actually only going to be having a right-tailed test. All right, or I can think about it that way. So when we look at this F distribution, it's not going to be, there we go. So if I think about this F distribution or different F statistics, it's not going to be symmetrical, right? In fact, it's going to have a really long right tail, right? Really short left tail, really long F. But we're still doing the same thing. It's just now, when we look at this test statistic, it's really going to be telling us the difference between that regression where we included the two variables and the one without it. So when we calculate our F statistic, the probability that we reject, right, or kind of that area to the right, even though we shouldn't be, this is now going to represent all of alpha. Okay, so we won't have two tails, we're only going to have one tail. Okay. So whenever I find that F statistic, I'd really be looking for just the area to the right. And I'm not going to make you use this F table by hand, but I'll kind of show you some things from it in a second. Okay, but the same kind of principle applies. So sorry, I said this is alpha. This would be if we're looking at our critical values for that F statistic. Once we find our actual F statistic, we want to compare to alpha, but the area to the right of that is actually going to represent our p-value. So the same kind of thing would happen. So if I don't put these, I'm drawing this a little bit more appropriately here. So here would be my critical value that gives me alpha total in this tail. I still want to compare that to whatever test statistic I have. It's just now it's not a T statistic. It's coming from the F distribution. So I would still want to say, okay, if that F statistic is greater in absolute value than my critical value, I reject. Same rejection decision we made when we're doing individual significance. Now the area to the right of my F statistic is my p-value. So if my test statistic, which is now coming from the F distribution, if it's ever greater than my critical value, what has to be true about my p-value relative to alpha? If I'm going more into the tail, what's happening to that area to the right? It's getting smaller, or that p-value is less than that desired alpha I set. Okay? So it's the same principle behind what we were doing before with individual significance. It's just now instead of two tails, we've got a one-tail test. Okay? Now, how do we calculate this F statistic is going to look a little bit different. All right. So why are we using a one-tailed test? Because we know when we add in variables, we have to see the R squared increase. So our F statistic is going to look something like this. Now, don't worry about this for a second, because I'm going to show you an easier version of this. Okay. So instead of, here, I'm going to skip ahead a little bit. So we kind of already talked through some of this. So if I have this joint significance test where I want to test for whether or not both coefficients are equal to 0 at the same time, I can rearrange this F statistic to be a little bit more friendly, right? So this we will have on that formula sheet. This is going to be the one that's a little bit easier to use, right? Now, what is that RSSR and USSR? It's basically the error or the residuals that come from both our unrestricted model, where I included all three variables, to our restricted model, where I only had the one. Now, anytime I have the errors, I can always rewrite that not as the proportion I can't explain, but I can rewrite it as the proportion I can explain, which is the definition of our R squared. Okay, so I'll have these two models, one where I've included all three variables. I could run that regression in Stata, get the R squared. I then have my restricted model, just the one variable on that right-hand side, run that regression, get my R squared. So basically, this is telling me how much the R squared went up when I included those two variables in my unrestricted model where I didn't leave anything out. Now, the base is going to be 1 minus R squared from the unrestricted model, which what would this represent? If R squared is the proportion of the variation in Y I can explain with my unrestricted model, what's 1 minus that? The proportion I can't explain, right? So it's kind of this ratio of how much did my R squared change by using this unrestricted model relative to what can I still not explain with it. Now we're going to scale that a little bit because as I add in more variables, what do I know is definitely going to happen to this difference? If I add in more variables, the R squared has to be going higher and higher, whereas in the restricted model, that just stays the same. So we want to penalize ourselves essentially for adding in more variables. That's what Q is going to represent. It's the number of restrictions or the number of variables that we're adding in to that unrestricted model relative to the restricted one where we left some of them out. In my example, it was just 2 variables, but we could test the joint significance of 3, 4, 5, 6 variables. So Q is going to represent that number of variables that we've included in the unrestricted model. Now, N is still our sample size. K is going to be the number of variables that we've included total in our unrestricted model. So it's not just going to include those restrictions, it's going to include those restrictions plus whatever other controls we already had in the restricted model. So in my easy example, as my earlier example, I just had 1. Right? So K would have been 3 because I had 3 total variables. I was leaving out 2 of them. The original, kind of number of variables I had was 1. But I can include several controls there. Okay. So we're going to use this equation, kind of think through how Q, N, and K is going to change things for us. Okay. So the stuff I skipped through, we'll kind of revisit because I wanted to show you that easier version of that F statistic. Okay. Because we don't have to use this version. In fact, I'm only going to ask you questions using the second version because it's a little bit more user-friendly. Right. So when we look at these F distribution, I kind of said it was one distribution. Technically, it's a bunch of different distributions. For any number of restrictions and any different sample size, or N minus K minus 1, those are going to be what we call our degrees of freedom. So usually our degrees of freedom was N minus 1 when we were just looking at one statistic. And then when we started looking at linear regression, it actually became N minus K minus 1. So we're still going to have that N minus K minus 1 as one of our degrees of freedom. But the other is going to be the number of restrictions that we're looking at. In my earlier example, it was just 2, but it could be, like I said, 5 or 6. So every combination of degrees of freedom is actually going to give us different critical values, which would correspond to having a different rejection decision made, even using the same F statistic. So once again, I'm not going to kind of focus on making you use this table, but if we had, let's see, do I have it pulled up here? Did I minimize it? Oh, where are we at? Well, looks like I didn't have it open here. So we'll go 371. Pull up my F table here. So it's going to look something like this. So notice every combination of degrees of freedom produces different critical values. Well, that's a headache, right? Now you'll notice as I start to get larger and larger degrees of freedom on both directions, this value, if I wanted a desired alpha of 0.05. So all of these would be the critical values for 0.05. So if we looked at kind of the value that gives us that from our t distribution, that would be what? I think 0.05 is going to be 1.645, right? Because that gives me 0.05 on each side, right? So here, our value is getting closer and closer to 1.645. As those degrees of freedom goes up, our critical value is getting smaller and smaller. If we have a large enough sample size, essentially we start to get the same values from our F distribution as we would from the t distribution. So I won't make you use this table, but that's kind of what's going on behind the scenes. We're going to use stata to simply tell us what that F statistic is, okay? And then a corresponding p-value. So when it comes to the F distribution, we're not going to use the critical value approach. We're just going to use the p-value approach. I'm not going to have you worry about finding the critical value and comparing that to our F statistic. We're just going to have to look at the p-value, okay? So it makes it a little bit easier for than what we were doing before. So go back to the slides here. Okay. So the problem is when we're looking at this F distribution, if we use the student t, we're actually going to be finding the wrong p-values. They'd actually be smaller than what they should be if we use the F distribution. So if they're smaller, we're going to be more likely to reject making the incorrect decision. Okay. So we're going to end up seeing kind of what this looks like in stata. Really pretty easy for us to avoid this mistake. So we had that different version of the F statistic. We now want to think about kind of this joint hypothesis testing, right? So here, if I had a model that looks like this, where I'm trying to predict GPA in that first year of college based off the person's age, their high school GPA, and a dummy variable for whether or not they were identified as female. Okay. So I run this regression and I get the following output. Right? This would be what we call our unrestricted model, right? It includes all three variables, right? So I get the same, I get my coefficients. I can look at my R squared, which is what, 0.1958. Now, I included a command here to just kind of limit so we're not worrying about the adjusted R squared when we calculate the F statistic. What did the robust command do? Do you remember? It adjusted for heteroscedasticity, right? So I'm kind of adjusting for that already. So we're kind of just comparing apples to apples. We just want to look at the R squared values. Now, so this would be, actually, sorry, this isn't the unrestricted model. Here I made it even more complicated. I forgot. So here would be my restricted model. I've only included three variables. If I instead include the same three I was before, but also this math science credits that they took in high school, or actually I think the number of math science credits they're taking in that first year of college, and then whether or not they work, right? And here's where looks like I made some typos as I was copying and pasting. We can't have three beta 3s, right? This should be beta 3 and beta 5, okay? So that makes a little bit more sense there. So when I'm including all of those variables, this is going to be what our unrestricted model is. It includes all five. The restricted model, we are only including those first three. So what should happen to my R squared? It should be included two additional variables, so my R squared should be higher. Sure enough, it's 0.1997 instead of 0.1956. So it didn't go up by much, right? But it did go up, right? So what we really want to do with that F statistic is say, okay, it increased, but not by much, right? And that could have just been luck. So am I explaining more of the variation in college GPA with these two added variables, right? Are they jointly or simultaneously significant? Okay. So what we would do is we have our F statistic equation. We could plug in the unrestricted R squared, plug in the restricted R squared. That difference should always be positive. When we have no restrictions, we include those additional variables, our R squared should always be higher. Then we kind of had how many restrictions did we have? Well, we left out two variables. And then I think our sample size was something like 1,400. Now, K is the total number of variables that we had in the unrestricted model. So how many variables did we have when we didn't leave anything out? 5. We don't include the constant here, right? It's just that number of variables we included on the right-hand side. And then we have to subtract 1. That's just part of kind of how we, just like when we were looking at even the sample mean, we divide by n-1 for that standard error, or for the, standard deviation of the sample mean, or if we're looking at linear regression, for the standard error, we had n-1, okay, from our simple linear regression. So we can calculate these F statistics. Now, compared to our typical critical values, is this going to be larger than those? So what were our kind of benchmark critical values for the 90, 95, 99% when we had a two-tailed test? That was 1.65-ish, 1.96, and then 2.58, right? Now, we can't really use those same critical values because we should be using the critical values that come from an F distribution. So we're going to circumvent that issue, right? And think about, okay, we can get Stata to basically, behind the scenes, determine what the correct critical values are, right? It's not going to show those to us, but it can use this F statistic and essentially find the right F distribution and tell us the area to the right, which would represent our p-value. So with this F statistic, we're not going to worry about the actual test statistic. We're just going to worry about the p-value. So as long as our p-value is less than alpha, we can reject. So can I reject here with 90% confidence? Well, is my p-value less than 0.1? Yes. So what I would say is the assumption is that those two variables had no additional joint significance or didn't explain any additional variation in that Y variable of college GPA. So I can reject that they had no additional explanatory power. Can I reject that they had no additional explanatory power at the 95% level? Yes, right? That's less than 0.05. With 99% confidence, can I say that these added variables actually increase the proportion that I could explain of college GPA? Not quite. right? My p-value be less than 0.01 there. So it's kind of like before. When we're looking at a coefficient, we're assuming it has no effect. So in these models, we're assuming that simultaneously these added variables had no effect. If we can reject that, we're saying they did have additional explanatory power, or they did statistically significantly increase the R squared, right? Or there's statistical significance on the increase that they had on R squared, okay? So if I run this test in Stata, the simple command is you run the unrestricted model, so that included all 5 variables. You then use this test command for the restrictions you want to test the joint significance of. So here that was the added variables of these math science credits and whether or not they worked. This is what gave me that test statistic of 3.7 and the corresponding p-value of 0.0249. But once we have that p-value, the rejection decision is exactly what we were doing before. Okay. Any questions on this before we keep moving? Okay. So, Stata does a lot of work for us. We don't really have to worry about this. So I've got some additional work here. I wanted to make sure that we kind of thought through some things before we jump into Stata. Okay. So, if I have this F statistic, I have a marker that works. We said it's basically how is it changing our R squared from the unrestricted to the restricted model, right? Or how much did our R squared increase by including these additional variables? Now we know that if we include more variables, we can always increase the unrestricted model's R squared. So we wanted to scale this by the number of restrictions or the number of variables we were including in that unrestricted model. We then kind of had this base comparison down here. We won't worry too much about this because the things that I'm going to focus on are the following. Okay. The first is not too crazy. Just intuitively, if the added variables are increasing that gap between the adjusted and the unrestricted and the restricted R squared. So if that difference in the R squared values is going up, what should be happening to my F statistic? It's going to be going up, right? And in fact, it's even more so because if this goes up, I'm subtracting a larger number, I'm dividing by a smaller number, that would also increase the F statistic, right? So when I have these restrictions and I haven't left them out of the model, seeing a higher R squared from that unrestricted model should increase that F statistic, which does what to my p-value? If I have a larger test statistic, the area in the tail is getting smaller, which makes it more likely that I can reject the null. Okay. Any questions on that idea? That one isn't too bad. Now, if I add in more variables, right? So instead of testing the joint significance of 2 variables, I want to test the joint significance of 4 or 5 or 6, right? I have more of these restrictions. What is that going to do to this fraction on top? Well, if I'm dividing by a larger value, this fraction is going to go down. So what's going to happen to my F statistic? It's going to go down, right? If my F statistic is smaller, what's going to happen to my p-value? So just, yeah, we want to kind of step by step, but right, I heard some answers already, which is fine, right? But you're right, the p-value is going to get larger, which makes it less likely I reject. Now, the other thing we can think about, and this kind of goes along with all the other test statistics that we were looking at, if I increase my sample size, it's just intuitively, it should always be that I'm getting more accurate results. So if I increase my sample size, we can kind of think through intuitively what should happen. It means that that difference I found in the R squared is more reliable. So higher sample sizes should lead to smaller p-values and more likely for me to reject. We'll kind of walk through, hopefully that's the case. So if I increase n here, what's going to happen to this fraction? I'm dividing by a larger value, this fraction goes down. If I then divide by a smaller value, my F statistic is going to go up, which means my p-value would go down, making it, sure enough, just like all the other test statistics, more likely we reject. So we can think through how these three things are going to impact our likelihood of rejecting. Okay? I tried to use different colors here, but you can always kind of go through this thought process. Okay? So any questions on this here? So if I ask you a question on the exam, I'd hone in on one of these things, right? I won't give you like changes simultaneously in the sample size and the number of restrictions. It would just be kind of one or the other. Okay. Any questions on here before we kind of look at this in Stata? All right. So nope, I don't have it open. So let's go to my do file. I'm going to open up. Here we go. Right. So let's see. We kind of worked through all this last class. So I'm going to come down here to looking at this NCERDC Indiana smaller. Oh, sorry. Thank you. I'm not on the desktop. I need to make sure I switch this to laptop. There we go. So we're in that MLR week 7. We did a lot of this work last class. So we're going to scroll all the way down to kind of this code right here, line 113. Now my path is going to be set up, correctly, right? Because I'm on my laptop. So that's nice and helpful. I don't have to worry about working from IU OneDrive. So I'll try to get this as much as I can so we can kind of see the Stata output and then the code. So I think what I did here is I'm going to run this line of code for something we're going to do later on. So before we kind of keep going down here, I'm going to basically create a smaller sample size identifier so we can use that later on to see how that sample size does impact our rejection decision. Okay. So the first regression I'm going to run is I'm going to try to predict math scores on some standardized test using the grade level and just whether or not the individual is male. Okay. So I'm going to run that regression. And I see here, I get an R squared of 0.0041. So what have I likely done? Well, if I'm only explaining 0.4% of the variation in this math score, there's likely a lot of other variables that matter. I have a huge omitted variable bias probably in my coefficients. So I kind of started thinking about, okay, one thing that I don't know, I think maybe I've shown you this before, but just to kind of reiterate it, if you want to know what the R squared is, you can obviously look at the Stata output. That's going to help you on the exam, right? If you wanted to run the code to just kind of display that to you, so I don't want to worry about like hunting through all this, although it's not that hard, right? I could use this display command, and after I run a regression, E and then in parentheses R2 gives me that R squared value, right? And it gets out to a few more decimals, right? So I could even say here it's 0.11129 if I want to be really precise. Okay. Now, if I run the unrestricted model, where I included not only grade and this dummy for whether or not they were male, but I have 2 additional variables I included, which is, are they identified as an exceptional student? So they were in like, I don't know, honors classes or something like that. And then were they learning disabled, right? These seem like 2 variables that are going to be probably pretty helpful in predicting their math score. So I run this unrestricted model. What should happen to my R squared? I've included variables, so it should be higher, right? Now, in fact, how much higher is it? Quite a bit. Now, once again, if I don't want to have to keep moving my do file here, I could use that display command again with the ER2 and see, okay, it's 0.1084563. I got to be even more precise than I did here. I rounded the 4th decimal. Okay. So we now have our R squared from this unrestricted model that included all 4 variables. We also have our R squared from the unrestricted model that only included these 2. Okay. So if I calculated this F statistic by hand, I have my unrestricted R squared, my restricted R squared. How many variables did I leave out of the restricted model? 2. All right, my Q is 2 here, so I plug that in. Then 1 minus the R squared from the unrestricted model divided by n minus k minus 1. So where did I get those values? Well, my sample size in those regressions was 972. Remember, k is the number of variables total I've included in the unrestricted model. How many variables did I include total in an unrestricted model? All 4. Right? So that would kind of give me my F statistic. Now, this is where in Stata, if I use this display command, it basically just does the math for me, right? And shows me what the value is. So I don't have to like put this into a calculator, right? Now I can, and if you're thinking about the problem set, if you do this work by hand, that's okay, as long as you show it. But you can do the work here, just use display, and that's just the same as entering into a calculator, okay? So I'm gonna run that. I get an F statistic of about 56.6, okay? Now, when I run that unrestricted regression, if after I use this test command, so it says, I want to test for the joint significance of these 2 variables I added in. So I run the unrestricted model and I then use this test command. What this will do is it will, behind the scenes, run the unrestricted model, run the restricted model, calculate the R squared, sample size, number of restrictions, number of total variables k, throw it all into that equation, spit out to you the F statistic, and also tell you that p-value. You don't have to use the F table. It looks it up behind the scenes. So this is like a time saver, right? So if I run this, hopefully I'm getting the same value as when I calculate it by hand. Sure enough, I am, right? I mean, it's a little bit off, but that's because when I do it by hand, I have to round somewhere, right? So those roundings, especially when we're dealing with small proportions like several decimals, that could make a little bit of a difference. But you can see here, I'm basically getting the same F statistic. It's just a little bit, the error there is going to be rounding, because when Stata does it using this test command, it's being super precise. It is going as far out that I'm sure there's a limitation. I forget exactly what it is, but it's going out to a decimal. It's way further than what's being displayed to us. Okay. Is that making sense? Any questions on that before we keep moving? Okay. So what is my p-value associated with that F statistic? 0. Right? That's the probability I saw this F statistic or anything greater, or the area in that right tail. So what levels can I reject that these 2 variables, remember, the null is that these added variables had no joint significance. So what levels can I reject that at? All of them, right? So basically these variables are really good at explaining more of the variation in this math score, right? They are jointly significant. Now, I could also test for the joint significance. This is where it's kind of nice. If I run that regression where I have the unrestricted model, I could now test the joint significance, not of the learning disabled and the exceptional variable. I'm going to test it for the other 2. Now, here's where it won't always be obvious, but we can intuitively think about what is the likely result we're going to get. Well, remember, when we ran that restricted model earlier, where I only included grade and male, how much of the variation in the math score was I explaining? 0.4%. How much did those added variables of exceptional learning disabled, they brought it up to 0.1, so almost 10% more variation. So if I instead think about testing the joint significance of grade and male, well, they didn't explain a whole lot of the variation. If I do a joint significance test for them, do you think I'm more or less likely to reject the null than for those other 2 variables? Well, if the R squared, when I just included those 2, is really small, when I make a joint hypothesis test for when I add those into the model, do they increase R squared by a lot? Remember, at its core, our joint significance test is when I add these variables in, is it increasing my R squared at a statistically significant amount? So if they had a really low R squared variable when they were the only ones included, are they likely going to increase the R squared by a statistically significant amount? No. So it's more likely when I run this test, I'm probably going to see that I failed to reject the null. So if I do that instead, sure enough, my F statistic is smaller, right? So it's like moving to the left. What's happening to that area to the right, which represents my p-value? It's a lot higher. Can I reject that grade and male have no joint significance? Right? So we start out assuming they have no additional explanatory power. Can I say that they do? No, I failed to reject that, right? At every one of our conventional levels. Now, if I wanted to say with 80% confidence, then I could reject, right? But at our conventional levels of 90, 95, 99%, we can't reject the null there. So this kind of shows once I have this unrestricted model, I can start to do this joint hypothesis test for whatever variables, right? Combination of variables that are in that unrestricted model. Here we just did two different types of tests, right? For two different variables, adding in them simultaneously, right? Two different kind of tests. Okay. Any questions on that idea? Okay. Where are we at on time? So we got a late start. Okay. So here's where I want to show you some things that maybe we could think about. So I'm going to use this later on. So remember I said last class, we want to include, or maybe it was last class, might have been the one before. If I want to include a bunch of dummy variables, so usually this is like different education levels. I think in the problem set, I did different income levels. Here I have different race identifiers, right? So here I've got tons of different ones, but it's in this ethnicity variable, which if I look at the data editor, it's all text. I can't run a regression with text, right? So we said, what is our way around this? If we use this encode command, it takes that variable, identifies every single possible text value for that ethnic variable, creates a new variable called race ID, where it assigns every single text a number, right? And then essentially, I can use that in my regression later on using the IDOT command, and it'll create those dummy variables for me. So I had some people stop in for some help in office hours yesterday. You could go through and use conditional statements and create all those dummy variables yourself. This is going to be a much easier way where Stata can do it very quickly. Okay. So we'll use that here later on, but just for right now, we want to make sure we have a racial identifying variable that isn't just text. So we're going to encode that original text variable to create one where it just assigns numbers to different text. So this is where we're now going to start to look at things and kind of get a little bit more interesting here. So what did I do? I actually limited this to 100 here today instead of 500. So we'll kind of update that. I think my values will kind of be consistent with that. So what did we say earlier? Right. If instead of running that entire regression where I think it was what 972 observations, if I instead go to here, I'll set this up down here just so we don't muddy it up with all the other stuff we were doing. So here was my F statistic equation. So if I go from instead of 972 to 100 observations, what's happened to my sample size? Decreased. If I divide by a smaller number, what happens to my fraction here? Denominator is smaller, it's going to increase. If I'm dividing by a larger value, what's happening to my F statistic? Decreases. If my F statistic is decreasing, what's happening to that area in the tail, or what's happening to my p-value? It's getting larger. With a larger p-value, is it more or less likely to be less than alpha? It's now less likely. So we should see that when I run the same regression I was before, when I looked at that joint significance test for exceptional and learning disabled, I should now find a larger p-value. Okay, so we can run through this thought experiment by using the data, right? So that was why earlier I kind of created this small sample size variable where I just randomly selected 100 observations, okay? So we'll come down here and I want to run this regression where I'm looking at the same unrestricted model, but I'm now doing this for a small sample size, okay? Now, if I run this, right, one thing I can think about is, let's say now, oh, what did I leave out here? Before we had exceptional and we had both of these. And learning disabled. So if I want to test for the joint hypothesis, we want to do this for both. Right? So if I run this test, we said we should have now here I added on this additional kind of term. So I already ran this, but it was only using the smaller sample size of 100. So before, when we looked at that test, we had a p-value of basically 0. It should now be higher, right? So I'm going to run this test for the smaller sample. Oh, I spelled something wrong. What did I spell wrong? Someone help me catch. What am I looking at wrong here? Oh, let's see. There we go. Sorry. So the mistake I made was I didn't have that regression run already. So it isn't identifying the variable. I had to make sure I selected that code as well. So what's happened to our p-value? It is now not 0. It is 0.03, or it got larger. Now we can still reject at the 90 and 95% level, but we no longer can reject at the 99% level. Right? So here this kind of proves to ourselves that when we have these smaller sample size, it's going to be less likely we can reject. Or said differently, with larger sample sizes, it was more likely we can reject this joint significance test. Okay. Any questions on that idea before we push this a little bit further? Okay. Now, one thing I also wanted to point out here, just to kind of, once again, we'll start revisiting some old concepts that we talked about. So we can do this joint significance test, but also we can compare something else we talked about. So when I'm running these models, our adjusted R squared was always what? Well, 1 minus, and this represented the errors, right? The sum of the squared errors, what we weren't explaining over the total variation. So this was kind of like the proportion we can't explain. And then we were multiplying that by this scaling factor of n minus 1 times, or sorry, over n minus k minus 1. So if I'm looking at a smaller sample size, this is where it's not quite clear, but I think it helps if you put numbers to this. So if I was thinking about the adjusted R squared, I would always use these numbers in this thought experiment. If my sample size was, let's say, 4, and I only had one variable as my explanatory variable, so I just had 1 here. Well, what would this be? If my n was equal to 4, this scaling factor would be what? 3 over 2? If instead I had a sample size of 100, what would this scaling factor be? 99 over 98, which is getting really close to 1. So as I increase n, what's happening to that scaling factor? It's going down. If I'm subtracting a smaller amount, what's happening to my adjusted R squared? It would actually be going up. Right? So that's with a larger sample size. The example we have in Stata, we went from like 972 to 100. So we had a smaller sample size. It's just going to have the exact opposite effects, right? We're just moving in the opposite direction. So hopefully when we look at this adjusted R squared for the smaller sample size, we should see that it is with a smaller sample, much smaller. Okay? So use this example to make a point. So let's say instead of scrolling up and down, I'm just going to run these two together so we can kind of compare the output. So if I run that original regression where I was using the full sample, I then run the regression where I'm looking at the smaller sample. We said the adjusted R squared should be even lower, right? So hopefully when I do this, I get, okay, my adjusted R squared is 0.1048. Oh, my adjusted R squared now is 0.06, right? That smaller sample size decreased my adjusted R squared by quite a bit. Now, what impact did it have on my R squared? It looks like it changed a little bit here, but really in theory, if I were to take an infinite number of samples, the average R squared I would see from that infinite number of samples would be what I found from the original population data set, right? It's just that we only have one sample here, so it's going to be a little bit off, but right, not much, right? On average, we're going to see kind of that same R squared value, but we know when we take a smaller sample size, that's going to decrease my adjusted R squared even more. Or if we go in the opposite direction, when I increase my sample size, that's going to increase my adjusted R squared, right? You make it closer to that actual R squared value, okay? So that's kind of an old concept I just wanted to revisit here as long as we had some of this regression output. So any questions on this before we keep moving? Kind of took a step away from joint hypothesis testing. Okay. So the next thing we'll take a look at is we're going to come down here. So once again, I'm going to go to run this regression where I had the small sample size just to kind of make this point here. So I've got my small sample regression. I'm then going to run this regression where I'm still limiting it to the smaller sample size. So now we're like fixing n, right? We're making it the same. But I'm going to include all the controls for race, right? Using that IDOT command. So I don't know how many races are in the identified here. It's like 4 or 5 or something like that, right? We could obviously make this into like more categories, but whatever the data had, it's going to create all these dummy variables, okay? So what am I doing here? I'm increasing what? So if I add in more variables, when I'm looking at this adjusted R squared, what have I actually increased? We said we kept the sample size the same. Heard someone say it, we're increasing K, right? So when I add in more variables, what's that going to do to my denominator? Well, if I'm subtracting a larger value, that means this denominator is going to get smaller, which means this fraction is going to get larger. If I subtract a larger value, my adjusted R squared is going to be going down, right? This was the idea that the adjusted R squared penalizes me for simply just throwing, stuff at my regression, right? Just throwing in as many variables as possible, okay? So if we were now to go back and compare to when we didn't include these racial identifiers, when I do include them, I'm increasing K. Sorry. When we do include these racial identifiers, I am increasing K, right? So I'm including more variables. What should happen to my adjusted R squared? It should go down, right? Now here's where we have to be careful. There was one other thing that when I included more variables, yes, that's impacting K, but if the variables matter, what else is being impacted? So as I add in more variables, what's happening to the proportion of variation I can't explain? The proportion I can explain would be my R squared, so that should always go. So what's going to happen to the proportion that I can't explain? Well, if I can explain more variation, the proportion I can't explain is going down. If I subtract a smaller value, what impact is that going to have on my adjusted R squared? So I actually don't know what's going to happen, right? I don't know what's going to happen to my adjusted R squared because when I include these variables, they could be good variables. They could have a lot of explanatory power, in which case that's going to increase my R squared and my adjusted R squared. But by increasing the number of variables, I'm also kind of creating this difference in my scaling factor, which is going to decrease the adjusted R squared. So this is like where in a question, if I were to ask you this, I would say something like, and I think there was a quiz or problem set question, assume you find the same R squared, or you assume that when you add in these additional variables, the proportion you can't explain stays the same. Well, if this did stay the same, we know that adding more variables will lower the adjusted R squared. But it could be that those variables decrease that proportion that we can't explain. So we'll take a look and see if that is the case in this example. And we'll do that by now running the regression where we include the race identifiers. So I'm going to execute that line of code. we're going to look at before I had an R squared and adjusted R squared of what? 0.1 and 0.06. So a pretty decent gap in between those two, right? Now I included all of those racial identifiers. It didn't actually lower my adjusted R squared, right? Because when I was adding them in, what must have been the case, they had a lot of explanatory power. So because that hey, and then the proportion I can't explain are pushing it in opposite directions, I don't know what's going to happen to my adjusted R squared. Unless I gave you like the added assumption that that proportion that the added variables explain kind of stays the same, right? But in practice, that's an assumption that's likely going to be violated. As we add in more variables, we know that that R squared, or the proportion that we can explain, goes up. Proportion we can't explain will go down. And so there, if you want to think about it, it's almost like I have these two arrows. In this example, what must have been the case? Well, when we ran this regression with added variables, K was lowering my adjusted R squared by a little bit, but having these additional variables decrease the proportion I couldn't explain or increase the proportion I could by so much that that's the effect that kind of won out, right? Or that's the effect that kind of drove the final result. Is that making sense what I'm saying? Any questions on this? Okay. So once again, we're kind of revisiting some old stuff away from joint hypothesis testing here. This is kind of starting to be review. And I'm going to keep doing this all class because I'm in the, I have kind of rote memorization of what I have to click. Okay. So we're going to come down here. I'm going to go back to the original regression and just kind of make a point here that regardless of my K or regardless of my N, as I have larger sample sizes, that difference between the adjusted R squared and the R squared is going to get closer and closer, right? So in fact, even with a sample size of almost 1,000, what's the difference between my adjusted and my R squared here? Really, really small, 0.006-ish, right? So as I have larger sample sizes, that gap in between my R squared and my adjusted R squared is going to be getting relatively small. Whereas when I had small sample sizes, right, there the gap was what? 0.08, right? Compared to 0.006, right? So higher sample sizes will kind of reduce that gap in between my adjusted and my regular R squared. Okay. All right, and the next thing we want to talk about is I'm going to come down here. We really kind of already looked at this, but now what's going to happen? So I'm going to go back once again, just so we don't have to keep scrolling. And you could scroll and that'd be fine. But I want to do this here just to kind of compare and contrast. So let's say I had our original unrestricted model that only had those 4 variables, right? We then did a test for exceptional and learning disabled, right? So if I run this, we should see, I think it was at 3.57, or no, sorry, this one was 56. So this is one where we had a really low p-value, right? Now, if I run the same regression and I want to test for the same joint significance, but I'm doing so by now including more variables here, right? So once again, if I include more variables, if we go back to our F statistic, right? So as I include more variables here, what's going to happen? All right. Well, K is going to go up, right? I'm just adding in more controls, even though I'm looking at the same number of restrictions. Okay. So here, one thing we didn't talk about before was what is the role of K, right? So here, and we'll kind of write this out just so we don't have to kind of have as many things going. So here's my F statistic. Here's my R squared. Restricted, unrestricted, divided by Q. 1 minus R squared from the unrestricted model. divided by n minus k minus 1. So here, when I run this regression, we have the same sample sizes, but in the unrestricted model, I now just have more explanatory. I have all those race dummies, right? So that's going to do what? That's going to increase k. Okay. I have more variables on the right-hand side. It's going to increase k. If I'm subtracting a larger value, what happens to n minus k minus 1? It's going down. If my denominator is smaller here, what happens to this fraction? It goes up. If this denominator is larger, what happens to this fraction? It goes down. If my F statistic is lower, what happens to my p-value? And I should be less likely to reject. Now, what's something I kind of forgot about here? As I add in more variables k, what's going to happen to my r squared? It's going to go up. Now, ultimately, why doesn't that matter? If I'm running a joint hypothesis test for the variables of exceptional and learning disabled, in both the unrestricted and restricted model, I'm now including those race dummies. They're not restrictions. They're in both of these models. So I shouldn't see that there's any difference in the restricted and unrestricted model because I've included these additional controls, because they're not the ones that I'm doing a joint hypothesis test for. So we shouldn't have to worry about the adjusted r squared changing, or the r squared from restricted or unrestricted model. Those shouldn't change at all. It's simply that we've included more controls when we're doing this joint hypothesis test. If we were doing a joint hypothesis test for the race dummies, well, then all bets are right. Then things are different. Q, the number of restrictions is going to be different. But if we're just including more controls, when we're doing the same joint significance test, it should cause our p-value to go up, making it less likely we can reject. So here, we started out with an F statistic of 56, p-value of 0, when I didn't have those race dummies. If I do the same joint significance test, the same two variables, but I now include these additional controls for race dummy, I've essentially increased k, which should do what? Should increase my p-values, but they're both 0. Even if you got this output and I gave this to you on the exam, why can you tell me you know what's happening to the p-value here? Even though it looks like it's 0, which of them, what would I kind of look at to determine? Oh, sorry. I didn't hit the projector. I actually only hit the audio, so that would help, right? So here I ran this regression, did my joint hypothesis test for the variable that, for the regression that didn't include those dummy variables, right? So I run that, I get this F statistic and this p-value. Okay. I then do the same regression, same joint significance test, but I now include the additional controls of these race dummies, right? Now I see, oh, with the additional controls, we said k would go up, my p-value should go up as well, but it looks like it's still 0. Why, if I gave you this output, could you tell me you know which of those p-values is lower or higher? What does that p-value come from? So we said our alpha is always going to be associated with what? So it doesn't matter if we're looking at an F distribution, or we could even take this all the way back to thinking about individual significance, right? So this could be a T or an F distribution. Now the F distribution, we're only looking at one tail, but you can think about it this way. Whatever my critical value is, if I only have a one-tailed test, the area to the right would be what? Alpha. The critical value is what gives us our desired alpha, our desired type 1 error in that tail. If I'm looking at my test statistic, doesn't matter if it's a T or an F, right? It's just coming from a different distribution. So it's still kind of a test statistic, whether or not we're doing individual significance or joint significance testing. That test statistic is associated with what? What's the area to the right of it? My p-value. So when I go back to that output, which of them is going to have a smaller p-value? The one that has a larger test statistic. So what did we say? No, I don't know where I put it. What did we say here? When I increase K, it should have a lower test statistic and a higher p-value. So even though when I look at that stata output, I can't see that there's a difference when I just look at the p-value because rounded to the fourth decimal, it's still 0. But which of these do I know has a larger p-value? The one that has a smaller test statistic. So here, what happened when I included more variables K? The test statistic went down. Now it's still very large, right? But it did go down, right? So even if we can't see the difference in stata output, this is the importance of, yes, we can run all this stuff in stata, but we still have to know what the underlying statistics are telling us. Because if we just look at the p-value, we're like, oh, both of them have the exact same statistical significance. Well, not quite, right? Because we can see that one of those test statistics is smaller, we know that's the one that's going to have a slightly larger p-value. And even though it didn't increase the p-value enough to change our rejection decision, with maybe smaller sample sizes, it could. So this is kind of, I don't know, just to make that point of that we don't have to just rely on the p-value. Even for joint significance testing, we can think about what gives me that p-value is whatever that F statistic is. Okay. Any questions on that before we keep moving? And I just have another example here where we could kind of run the same thing. I won't kind of waste time on this today. So we only have like 8 minutes left. I think I'll give you a roadmap kind of for where we're going, right, to end class here today. So on Thursday, I have this STAR public use data set. To be honest, it's a lot of replication of what we did today, just with different variables, right? So I'm probably going to skip through this. We might revisit this one. I'm actually going to start on Thursday's class with this powerlifting example, and we'll think through some joint significance testing, just because that's like the newest thing. We want to make sure we do a little more work with that. We'll also then talk about how do we calculate biases that might exist, multiple dummy variables, the issues of perfect, imperfect multicollinearity. So we'll probably be on Thursday going through more of the recent material, stuff from last week, and then joint hypothesis testing. And then when we come back next week on Tuesday, that's where anything's fair game. So if you look at that practice exam and you have questions over anything, make sure you're bringing those questions. We'll probably have some time on Thursday's class where I can answer some of those questions, but definitely on Tuesday, all we'll be doing is review. Okay. Now, what I'm also going to do, just to give you an idea about how this exam is going to look like, I had some people stop in yesterday and ask this question. So let's go here. This is the practice exam that I gave you. So first of all, and I think this was a question that was asked, you will have this formula sheet on the exam. So this is every formula that we've talked about that you would need. In fact, there's some on here that you probably might not necessarily use a whole lot, right? But it's anything that we've used that you could potentially need, okay? So you'll have this formula sheet on the exam. Now, if you're looking at these practice problems, it goes all the way back to when we first started looking at testing means, right? That was like the initial thing. We kind of did a lot of review. Now, there won't be a lot of questions thinking about covariances, skew, doing a test statistic for whether or not the mean was different than a certain value. But there will be a handful of questions there, kind of starting out with some of that, shouldn't say easier material, but kind of what we had to start with to then build on its, to get to linear regression. You'll notice here already at question 4, I start using simple linear regression. So this practice exam, the breakdown should look pretty similar to what the actual exam is. I write this to kind of give you the same level of difficulty as what the exam will look like. Now, any question on here, and kind of the same breakdown of like how many questions are coming from like simple linear regression, multiple linear regression, all the different topics we covered. So I'll have those probably printed on the first sheet of the exam. So that will be kind of our 3 benchmark values. I'll have those critical values will be on there. Good. That's a good question. So this is going to be a really good roadmap. Now, if you're looking at this practice exam, there's going to be some questions that are multiple choice, but a lot of them are going to be fill in the like short answer, right? So any question that's on here, if I make it multiple choice, for most of them, I could likely make it kind of a short answer question as well, and vice versa, right? So I'm not saying that this practice exam, not every multiple choice question you see would be a multiple choice question on the exam, and not every short answer would be a short answer, right? They could flip, right? What I'm going to do, and I don't have the exact point breakdown quite yet, I will know it for sure by next Tuesday's class. Still kind of finalizing some things based off of what our discussion is in class and a little bit based off what we talk about on Thursday. So I usually have these exams to be, kind of behind the scenes, pretty much ready to go. But I obviously want to have them like based off of what we've talked about a little bit more. I try to make sure I have the exam reflecting more of that discussion. So I'll kind of wait until after Thursday's class to finalize things. I'll give you the point breakdown next Tuesday, but it's going to be roughly 25 to 30% of this exam. I'm actually going to make a take-home exam, right? So this will be done through Canvas, and those questions are going to be multiple choice and like formula based. You actually have to come up with a numerical answer to. Now, the reason why I can do that is because I have banks of questions and I can generate random numbers so that I know that no two of you are seeing the exact same take-home exam, right? So that's a way that I can kind of feel okay with that, right? But on that take-home exam, you're going to have available to you what? All of the materials from the course, right? Now, the in-class portion, once again, will be about 70 to 75%, so higher weighted, and it's timed, obviously. Now, the take-home portion will be timed as well. Once you start, you'll have like 60 minutes to finish it. But this in-person exam will primarily just be short answer, right? And that take-home will be the kind of multiple choice, kind of formula-based questions that you could see, okay? And as we work through more problems, I'll kind of mention some of those, what might be on the take-home versus the short answer in class.
So for the exams, we won't be coding in this data. We're just using that.
So once again, these practice exams, very similar to what you see. I don't make you code. I'll show you the code and I'll show you the output. You then have to know how to use that output to answer the question. Now, sometimes I might give you the output, but leave out certain things. That requires you to know something more about the concepts in order to answer the question. But yeah, you're not going to be like tested on specific coding. Now, before you get ready, packed up, and head out of here, I'm going to give you another suggestion when you're studying. I actually, right before class and after, I'm in some courses as well, looking at generative AI tools, right? How to employ them in the classroom and how to use them, right? They're helpful. And I'm guessing some of you have used these on the problem sets, right? It can be helpful in coding. And the reason why I know that some of you are using them is because you're using commands that we didn't cover, and it's likely the result that a chat GPT or something would give you, right? Some of you have lost points because one thing that chat GPT is really bad at still is identifying difficulty of questions. And so when it's pulling things from the web, A, there's things out there that are wrong, right? B, the assumptions that we make in this class, this is introduction to applied econometrics. We don't make those assumptions when we're looking at more difficult material. So when it goes out and grabs things from the web, it grabs everything. Things that are out at a level of difficulty higher than this class, and things at a level of difficulty lower. So sometimes it'll give you answers that would be wrong for the level of difficulty or the assumptions that we have in this class, right? So it's okay to use this generative AI tool when you're thinking about creating questions to study. But based off of my experience and playing around with it, with my course materials, I'd be kind of hesitant with that because it gets things wrong a lot more often than you think. And I don't want you to have an inflated sense of like, oh, okay, I'm memorizing exactly what ChatGPT or whatever is telling me. It could be for a much higher or much lower level of difficulty. So I have created this practice exam to be reflective of the level of difficulty of the exam and the types of questions you'll see, right? Now, if you're feeling really comfortable with that and you want to run it through AI, I mean, you can, but I can't guarantee that those questions are going to be answered correctly or are even going to be the exact same thing that we're doing here, okay? But other than that, I think that should take care. Sorry for the weird start. Second or third time this semester I've had issues up here, so I'm going to have to call them. You can see how helpful they were at the beginning of class, so I'm sure I'll have some fun this afternoon. But I will see you guys on Thursday. We'll just be doing more review. Okay? Here, give me 1 second. I want to make sure I stop this recording.